I'm Matt from Motorsport Electronics, and in this brief video we're going to do a deep dive on the engine driver and what some of these settings mean within the ECU. So first up we have our trigger pattern. This is the crankshaft or the base pattern that we're going to reference. Some engines use a camshaft position sensor as their primary pattern source. Again, it is the primary reference of the position of the pistons within the engine. We have an array of different modes from MX5NA through to K20, Nissan RB, Rover T series and so on, 36-2. We're on a Ford Fiesta at the moment, so we will set this one to 36-1. The trigger edge is typically determined with a VR sensor on the way it's wired. The VR sensor, as you recall, will produce a varying AC voltage. We are choosing the edge upon which we trigger. Are we triggering as the voltage passes the 0 point in a positive direction, or are we passing it as the voltage point drops below 0? That would be determined either rising or falling. And some other sensor patterns which use Hall effect may require both edges. That is specific purely to the engine, and you can obtain those from the base maps for the engines we have produced, or with a combination of the trigger scope and using diagnostics, ascertain which edge works best for you. Cam sync after RPM. Some camshafts have a single lobe, and using an adaptive system, the frequency that signal comes in is not fast enough at cranking speeds to be able to facilitate an accurate sync, but the camshaft is needed to enable fully sequential or VVT control. For that reason, we have cam sync after RPM. The number you type in here is the RPM at which point we try and synchronize the camshaft. Typically that would be 1000 or 900 RPM, such that once the engine speed increases, we then begin to listen to the cam and the ECU will become fully synchronized to camshaft as well. Cam A and Cam B patterns, much like the base trigger pattern, allow us to tell what type of cam pattern we have. Is it ST150? Is it 1UZ? Is it MX5NB or NA? Is it single lobe, Subaru, and so on? And the Cam A and Cam B trigger edges, again, much like the crank trigger edge, determine falling, rising, or indeed in some cases both. Ignore cam after sync. Similarly to the cam sync after RPM, this is a setting that allows you to, once synchronized and discovering the number 1 TDC on a 720-degree cycle, we can actually say ignore the camshaft. We no longer need to listen to it. We have ascertained the position of our engine, so stop relying on that signal for synchronization. This is handy for engines that have a particularly noisy camshaft, but bear in mind you will not be able to use this if you are using VVT. If you are using closed loop variable valve timing, you need to monitor that camshaft at all times, so you will not be able to use this option. Trigger offset typically goes from 0 to 360 degrees, and it is in relation to where the missing tooth or the 0 point identifier on the pattern is in relation to the TDC of number 1 of the engine. On this particular engine here, we have 270 degrees we found with a timing light. It might be 90 for certain Fords, 180 for other engines, 120, it could be anything, okay? Trigger filtering should typically be left set to none. However, low and high determines the amount of time it will reject a signal. If you have a 36-1 pattern and half the time between the expected pulse and the actual pulse arriving, it can reject that signal based on light, and on low filtering, and on high filtering it is 75% of the time. It's like a false trigger rejection. Timing delay in microseconds in US allows us to say, look, when we fire our coils or we fire our outputs, there is a latency in hardware, and by putting a number in there we will compensate for this. As RPM increases, it will change this delay based on that amount, so we can change this number here in microseconds, and it just adds that base number onto all output configurations. And as I say, as RPM increases, this delay becomes more relevant, shall we say. VR Auto Adaptive. Now the ECU, the ME221 and the ME442, when using the crank or cam VR inputs, we have a Maxu input driver chip, which most other ECUs use as well, which allows us to automatically compensate for the voltages over time. When the engine is at a very slow speed, the voltage generated of those teeth passing that sensor at a slower rate is lower than when the engine is at a much faster RPM. And as a result, the chip will automatically take into account the last size voltage and use that as a threshold, or a certain percentage of that as a threshold for the next tooth. This helps with noise immunity. There are, however, some cases where in fact we want to simply specify the voltage at certain RPMs we want to use. To use that, turn the adaptive to no, and then head up to the search box, type in LVL to bring up the tables, and we can see the crank trigger level table. In here we can specify the voltage, typically between 1 and 5 volts, and the RPM at which it is relevant. So if we set this, for example, to 0.5, we are saying that at around 1000 RPM, do not trigger unless we see 0.5 volts on our waveform. We might then say at 7000 RPM, we want to see 3.5 volts. Selecting between the two and pressing Ctrl W will interpolate those as you would expect over RPM, but of course you can tune those as you see fit. And I'll just press save to store that to the ECU. The sync start and sync loss multiplier are relevant for multi-tooth patterns. With sync start, what we're saying is that the gap needs to be at least 1.3 times the nominal tooth size. So as our trigger wheel is spinning around, we are on our 36-1, we have 35 teeth of size 1, and we will not consider a missing tooth unless we see a gap at least 1.3 times. The sync loss is similar in that if it sees a tooth below that, it will then reject the synchronization. So it will say, hang on, we were expecting at least 1.5, we saw, or sorry, 1.3 in this example, we saw 1.2, so reject the sync. Moving on to algorithm configuration, primary load and secondary load. This determines our mode of operation, either alpha N or speed density. At the moment, I'm in a speed density configuration where I'm using manifold pressure as our primary load source, and I'm using TPS as a secondary load. And we can use those in trim tables to apply secondary loads based on throttle. Very handy for things like supercharged cars, where manifold pressure could be varying quite a lot and we need a bit of TPS oversight. Displacement, fairly explanatory, 2000 cc's for this particular engine. It can also be used as a very coarse fuel trim. If we're running this engine up and we think it's very lean on this base map, if we add 10% to that displacement, for example, change it to 2200 cc, then the ECU will put in 10% extra fuel because it believes it's just been fitted to a bigger engine running the same fuel map. Number of cylinders, self-explanatory, and I would also consider firing order to be self-explanatory. I hope you found this deep dive useful, and remember, you can always click on the question marks or the big question mark at the top to bring up the help files for more details. Thanks.